So good morning, good afternoon, and good evening, ladies and gentlemen, depending on where you are in the world. It's my great pleasure as the European Section Chair to introduce you to today's webinar, the first in our series of 2022 webinars on the basics of respiratory protection, the what, the where, and the why. So just as a webinar introduction, I'm going to give you an introduction to ISRP, what is the organization, and then we've got three internationally outstanding keynote presenters who are going to talk about a range of topics from respiratory physiology, the fundamentals of filtering respiratory protection devices, and lastly, but not leastly, we're going to talk around self-contained breathing apparatus and connected safety systems. And then at the end, we will have our usual Ask the Expert question and answer session. So a bit of housekeeping, if anybody has any questions as we go through the presentation, I will be vetting them as chair. Put them in the question and answer box within the Zoom function, which you'll find at the bottom of your screen. And then at the end, we will bring the presenters together as a collective to answer any collective questions that there may be after each individual presentation. So without further ado, so I'm keen to introduce you to, if you've not heard of us before, we are the International Society for Respiratory Protection. We are a non-profit organization, and our charter is to provide education and information to all individuals involved in respiratory protection. We have 6 sections. Today's section is covering the European work, but we have sections in Australasia, Japan, Korea, and Greater China. And we all have and uphold the same objectives of the society: to enhance health and safety of persons that use respiratory protection. But we also encourage the development of standards, best practice, and the exchange of information, whether you be a government entity, organized labor, education, or just anyone interested in the use or development of respiratory protection. And we work with many manufacturers and professional organizations around the world. So our education program, this is our second year in operation in terms of a webinar series. And the aim of the webinars and the education program is to introduce attendees to respiratory protection in response to airborne hazards, the lessons learned from working in such environments, and the technologies used and how we can measure to respond to such threats. So at the end of each workshop, you will appreciate as an attendee the types and risks, including pathways and symptoms of working in such environments, depending on the topic, and understand where respiratory protection fits in to your hazard assessment and where it can be used and cannot be used. And we do that through a series of case studies and keynote presentations. So without further ado, I will introduce our first keynote speaker, Dr. Dan Wakanda, who is Senior Research Engineer at the US Navy Aerospace Medical Research Laboratory. And Dan is kindly going to give us an in-depth overview of why humans breathe and how airborne pollution can potentially affect them. So for those who don't know Dan, he has a wealth of experience in testing of respiratory devices, and he's been involved in regulatory standards at the very highest level for many, many years. And he's been involved in a lot of research in this area and holds many patents and publications. And without further ado, Dan, I will turn the floor over to you.
Well, thank you, David. I will share my screen so you can see vision. And indeed, my current work title is Senior Research Engineer. So you may wonder, why do I talk about respiratory physiology? Why do you say give a job to an engineer? Well, you can generally only have one job title. And the current one is obviously engineer, but I've also been working in the respiratory physiology lab at the University of Buffalo in Buffalo, New York for 14 years, as a research assistant professor there in physiology. So you can have more than one title, except there's only room for one on your hat. So this is my current work. I do have worked a long time with the interaction of people and their breathing gear. It's the way you breathe affects how the apparatus works, and the way the apparatus works affects how you breathe. Well, actually, yeah. So respiratory physiology, how and why do people breathe, and especially for this group, is in the presence of respiratory protective devices. And just to tie into what David started saying about ISRP, in the world today, there are many people who try to tear us apart, make us split, make us not be friends. But ISRP, to me, is just the opposite. It brings people together. We're working for a common goal, and I'm very pleased to be a member of it. And it's so an overview of what I'm going to talk about is, of course, why we breathe and what happens when people use respiratory protective devices or RPPs or breathing apparatus, or whatever name you want to call it. And we'll talk about the respiratory loads that are imposed by these RPDs and how much of them is reasonable. And how do we test for respiratory loads, both when you test the apparatus itself and the combination of people and the breathing apparatus. The effects of CO2, I'll go into that more detail, and some what happens when you breathe high levels of oxygen. So the basic needs of the body is when a muscle moves, it needs food and oxygen. Food in whatever you ate that day or the day before, and then the muscle will move, but it also produces CO2. Like any complete combustion, you take oxygen and some sort of source of energy, and you make heat and CO2. And the body controls breathing to maintain a steady level of CO2. Strictly speaking, it's the partial pressure of CO2 that is important to the body, not the percentage of CO2. And the movement of gas in and out of lungs dilutes the CO2 that the body produces, and we call it breathing. So the purpose of this slide is to show that we breathe to remove the garbage we produce. The purpose of breathing. And of course, we need oxygen. You've probably thought that was the primary reason, but it's actually a secondary. And while you move the gas in and out of your lungs, oxygen comes along by itself. The only exception to this is if you go to high altitude, where the partial pressure of oxygen is low, and then the body has a hypoxic response to that to bring in more oxygen. Otherwise, it's all controlled by CO2. Air contains about 21% O2 and has almost no CO2 in it. And when you exhale, you typically exhale sort of 16 to 17% O2 and 5 to 6% of O2 and 5 to 6% CO2. And strictly speaking, by textbook, it's a partial pressure of 40 plus minus 2 millimeters of mercury, or 5.3 or so percent. Okay. So if you now go skiing at the high altitude, say 3,000 meters or 10,000 feet, you still breathe 21% O2 because the air is well mixed and has the same concentration no matter where you go. But the barometric pressure there is only about 0.7 atmospheres. So you can multiply 21 by 0.7 and you end up with about 15%, equivalent to breathing 15% of sea level. And of course, if you go to Mount Everest, you have almost no barometric pressure, really, really low partial pressure of oxygen, even though it's 21% of. And of course, the harder a person works, the more O2 the muscles consume. And this obviously then also increases the production of CO2. So to maintain a constant CO2 in the body, more gas flow is needed to dilute it, breathe more, essentially. And of course, the harder you work, the harder the person breathes, and the harder the respiratory muscles also have to work. And we measure, of course, this as in terms of numbers, an increased minute ventilation. How much gas have you moved in a minute? And how much do you breathe? Well, you do need different minute ventilations for different workloads and how long a particular workload can be sustained. And if you're at rest, you typically breathe in the order of 6 to 10 liters a minute. If you work hard enough that you can do it for a full shift, 8 hours, you typically will breathe in the range 20 to 50 liters a minute. And for harder work, which you then can sustain for a shorter and shorter time, you will breathe more and more. So if you expect to have something that works, you can work only for 5 minutes, so very intense work rate, then you can breathe 90 to 100. These are very large numbers and may seem very excessive. But I actually had a subject once who maintained 140 to 145 liters a minute for an hour. He was an athlete, long distance runner of a very high level, performance level. And so it's not what you would find in daily life, but it's possible. And if you need more examples, you can look in this ISO document there. Other places too. So why do people use RPDs? And they are uncomfortable, they're warm, they can be heavy, they're bulky, they're in the way. They may restrict how well you can see because they stick up in your vision. But it allows people to enter places where we can't otherwise be. May it be smoke-filled buildings, you can stay underwater, in other words, go diving, you can go into space, and you take your personal environment with you, and you are in a protected zone. And nowadays, we can even go and buy groceries. You don't have to be heroic efforts to do this. You can go to the grocery store and hopefully avoid COVID or whatever comes next. But this ability to breathe is not free. It is hard to breathe. There is no free lunch. There is no free air. And RPDs can have both psychological and physiological effects. I won't talk much about psychology because it's not my field and that's not the topic of the talk. But people become very aware of the breathing. You put something over your face and you feel the warmth from your exhale air and the dampness from the moist gas. And it touches your face. You have very many nerve endings, very sensitive part of the body. Some people actually cannot tolerate RPD. There have been studies I've heard of in military use for gas masks, and maybe 10% of the recruits could not wear RPD at all. And RPDs make it harder to breathe. And these loads include flow resistance. You may have narrow passages in the mask, for instance. You have a filter that you draw the gas through to get clean gas. You have valves to direct the flow. You can also have elastic effects, as in a hose moves when you breathe, and a mask may pump on your face if there's high resistance. You may have its constant pressure, typically a slight positive pressure breathing for typically firefighter type breathing gear. They have a slight positive pressure. When you have a leak, you have gas leaving, good gas leaving, you're not inhaling the toxic gas. You also have then a volume in front of the face. So when you exhale, you fill that volume with CO2-rich gas, get rid of, and next time you inhale, you get some of that back, and that's called space. So obviously, breathing loads make it hard to breathe. And to get as much air as you did without an RPD, you have to increase your effort of breathing. Otherwise, you get less air. It's sort of like walking uphill. You need to increase your effort to walk, to maintain speed, or if you don't, you end up walking more slowly. And if you have less flow of air, you get less dilution of the CO2, and you get higher concentration of CO2 in the gas. Healthy people control their breathing quite well without an RPD, but with an RPD, it's not uncommon to see high levels of CO2. You can actually get low levels of CO2 also because people react differently to the presence of an RPD. And you may have odd or unexpected behaviors from your RPD. A valve can feel sticky, doesn't open until an extra effort has been spent, sort of pops open, and after that it breathes normally. And that may be one breath or maybe every breath. The function of the pressure regulator, if you have a SCBA as a self-contained breathing from a tank on your back, can be inconsistent. When the pressure in the tank goes low and it's almost empty, some regulators will raise the pressure and make it push gas into this. Others will make it really hard to breathe. And it depends on the closed circuit rebreather may have an empty or full bag. So when you exhale and the bag is full, you sort of can't exhale anymore because the bag. We may slam empty at the end of an inhalation. That may be a surprise. How much breathing resistance is reasonable? And it's often specified as peak pressures in a mask or mouthpiece. Go into historical reasons. I will give you some examples of what these are. And I started with a NIOSH as a US specification for breathers for escape. And I plotted here the minute ventilation on this axis, vertically the mask pressure swing. And for this particular device, you can have plus or minus 100 millimeters of water at 3 different ventilations. And if you add more NIOSH numbers, you see they are everywhere. And if you can be silly and say, well, so if somebody's breathing on this demand device, can only tolerate less than half the pressure in an escape device. Are people weaker because you breathe on a demand system? If you have a pressure demand system, you have almost twice the pressure allowance. And then you have other examples here. The gas mask is this one, and it's only half of what the escape device is. And it's not a sort of a US phenomenon. If you had some European standards, they also are sort of all over the place. And so how can the limits be so different when the same device, the same person could use each one? My muscles don't get stronger or weaker because I switch to. Some limits were based on, just turn off the camera here, seemed to work well when they were designed, and the performance limits, the performance of that particular device became the limit. Pragmatic approach. And you have to start somewhere, but you shouldn't stop. And I see this as people started somewhere, they seemed to work, and they kept going. It's not unique to occupational use. We have seen it in diving. We have seen it in military aviation. You start somewhere, but then you stop. So how does one determine acceptable? Is it just enough to ask if a particular RPD was easy enough to breathe? Sounds easy, doesn't it? But unfortunately, it doesn't work that way. And some people will simply not breathe enough. They will let their CO2 levels climb too high. And some people will have CO2 levels high enough that the CO2 becomes a narcotic gas, will affect their mental function. And these people are generally not aware. We run tests where people have maintained very high levels of CO2, high enough that they reached our abort criterion. And you ask them to stop, and you ask them afterwards what happened, and ask you, well, why did you stop me? I had a great workout. And they had no idea about the CO2. I mean, this is high work rate now, not something you would typically see in a daily use situation. It can happen. So I'm not trying to scare anybody for this. So to find acceptable loads, we need both subjective and objective measurements. So you can ask people, how difficult was it to breathe? Was it easy? Was it extremely hard? And the objective measurements can be then these CO2 levels and how much did it change the endurance of the person and the breathing capacity? And neither of them must be too high. So can you actually get limitations from wearing an RPD? And we did a study about 10 years ago, 12 years ago. We had people running on a treadmill at a high rate. We did 2 tests, once with an approved mask and filter, once without. And we had set the speed on the treadmill so people could run sort of 20 minutes was we aiming for. And we ended up with an endurance time of 23 minutes without the mask. And we put the mask and filter on, they could only do 10 minutes. So it dropped by 57%. And they said typically that it was a bit hard to breathe, but my legs gave up. And they didn't really know how much shorter time they ran with. And so without the mask, they breathe in the order of 110 liters a minute. So way more than you would do in an occupational situation. But with the mask, they could only breathe 87. And some higher than you would see, but nobody could really tell online that they were restricted. And also measured how much oxygen they consumed. So how much did the muscles want? Without the mask, the body wanted 3.7. And with the mask and filter, they only got 3. So the oxygen consumption dropped. And this caused anaerobic metabolism in the leg muscles, which produces lactic acid. Your muscles hurt, and people. Indeed, they could tell that the legs gave up, but not the reason why they did it. And the CO2 levels they maintained here entitled CO2 in a normal range towards the end of the test without the mask. But with the mask, they had very high levels of CO2. Some of them were in a narcotic range. That seemed fine, fortunately. And if you want a copy of this report, that's down here. You can email me afterwards and I will send it. I have an email address at the last slide as well. So the filter used with this approved mask was tested during certification at a constant flow of 85 liters. That's a technical way of testing a filter. Unfortunately, I don't know any person who actually breathes constant flow. I need to breathe in, I need to breathe out. So I never quite understood this testing. You may find out later today from the other speakers. And it shows that this flow originates in a measurement 1917 and 1918. Dig back a long way to find the original documentation for this, but it's only a table in that book, and the subjects were quoted as having been at the light run. And obviously, there was a mismatch between the tests we did, or the certification tests, and the actual use that we in this study. And the users typically don't know the conditions of certification tests. The RPDs don't come with a maximum speed limit sort of. And in the example here, the pressures in the mask were very negative. People really had to draw gas hard to get any. And the mask could not possibly have provided effect. And the limits so far have been described as peak pressures. And they are the highest pressures during expiration and the lowest pressure during inspiration. 2 points determine everything. How about everything in between? The average pressure, we actually look at every part of the breath. Reason for peak pressures is that when the limits were set, it was fairly easy to read peak pressures on a pen and ink. These numbers go back to 1920, 1940, 50, 60, 70, well before computers were around and you could easily do averages. You could read the swing of the pen with a ruler or caliper. They would have something of this nature where you have pressure and volume on the left. The blue is the pressure you inhale, and then you come back to inhalation ends here. You start an exhalation, positive pressure. You go up and down here for about 10 breaths. And you can draw lines here. Okay, that's the peak. Those are the peak pressures, more or less. And then you can transfer. Okay, that's about 1 kilopascal pressure swing. And then you say yes or no. And I would be very hesitant to try to figure out where the average would be in these signals just by eye. And I'm not even sure I have the peak pressures correct. So people have made determinations of acceptability based on only 2 points from the breath. And it certainly can provide some information about not reveal the whole. So nowadays, as I mentioned, it's easy to determine both peak and average pressures. Collect things, fantastic data rate, and you just calculate the age. So more recent work on tolerance to breathing resistance describes the loads in terms of work or breathing. And it's when we write these numbers down, it is actually the same as an average pressure, strictly speaking, volume average pressure. And since different muscles do the inhalations, the exhalations, the RPD must have separate calculations and limits for inhalations. You can then set limits based on a combination of average and peak pressures. I mind you have it all covered. So most, or even every country, has standards for RPD. You have the EN standards, you have the NIOSH standards in the US, CSA and other organizations in Canada, standards Australia, GISE in Japan, and so on. And some of them are actually copies of other countries. NIOSH seems to be one an early creator of these standards, and other countries have copied some of them. And it applies both to test methods and limits set. And as I mentioned, most or all are based on some hardware, and some human testing have been used. And generally, there's only one workload intended maximum. But 2 or 3 years ago, the International Standards Organization finished an entire set of new standards called the ISO 17420. And these are human-centered performance standards, as in no device-based. They all always the same number for a given minute ventilation, doesn't matter what system you're breathing on. And they can be intended for 4 different workloads. So if you're only going to wear a device sitting at your desk, working on a computer all day, it can be a small, lightweight for this light work, and possibly even cheap. But if you are going to need to breathe a whole lot, carrying heavy loads, you will have to have a larger device that lets you breathe more, and possibly costly as well. But the point is you can tailor the device to the expected use. There's not need for one size fits nobody. And the human factors documents are in this 16976 series, and the test methods go with them, or 100 series. So how do you calculate worker breathing? Before you saw the plot of volume and pressure against time, but if you now plot them against each other instead, you have pressure here, vertical axis, and volume on the horizontal axis. Start the inhalation up here in the upper right corner anyway. So you draw gas in, you lower the pressure in the mask, you go lower and lower. Typically, halfway through your breath, you have highest flow, so you get the largest pressure drop. And then towards the end of an inhalation, you slow down, and the pressure comes back. You exhale, it goes the opposite way. So you get a loop like this. And if you remember your physics, you see that the area inside this loop is work times volume is work. And you can then make it a rectangle instead of the odd shape you had before. And you can easily see inspiratory and expiratory work of breathing that you then can determine separately. Here you have the height of the rectangle numbers for that. And when you change the minute ventilation, the loop typically changes as well. If you breathe 35 liters a minute instead of the previous 65, you take a smaller breath, 1.5 liters, and the flow rate is lower, so you get a smaller loop. So obviously work is smaller. If you go all the way to 135, you typically would take a 3-liter breath, and the loop is more. And you can also neatly look at the shape of the loop. This is maybe more applicable for test houses and manufacturers. So here you have an unassisted filtering device. So essentially a filter mask where you have a lower, the pressure during inspiration is greater than expiration. So drawing gas through a filter, as you can see here. You put a fan on it to blow air through it or another flow of gas. So an assisted filtering RPD, you see the whole loop shifts up because you have raised the pressure in the mask based on the gas flow through it. And you may have other reasons to raise the pressure, so you have a good safety against breathing stuff from outside. You have a closed circuit device, and it may look like this. You can see the sticky valves here and here during expiration, one at least, or a firefighter type, an SCBA, where the loop is above 0 the whole time. It never goes negative. So each type of RPD has its own fingerprint. So to identify the key parts of a breathing loop, you can write for any time, any point on the loop here, say that the pressure is the flow times the flow resistance at that point, plus the volume change times the elastance, and you have a starting pressure drop based on flow would be here. The elastance is the slope of this line. You notice that the pressure here is not the same as the pressure there. There's an elastic component, in this case, a rebreathing bag that is held closed somewhat with a spring. Less compliance with that spring. And this is then the starting point. These 3 parameters you can explain the whole. And these measurements would typically be made by designers, manufacturers, test houses, or certification labs. It's not something you do at home in your garage. You need not very seriously fancy equipment, but they do cost a lot of money, and you also need to know how to use them. So how do you know that your measurements are actually correct? So you can calibrate your pressure, you can calibrate your volume sensors, but is the entire system giving correct values? Are your calculations correct? That should be easy, but how do you know? It's a simple way or device that can be used. Indeed, put crudely, it's a piece of steel orifice that is very simple to make. It was invented by the diving unit from the US Navy over 30 years ago. And it was later been adopted by the EN standards for use in diving, and ISO has also adopted it, ISO 6900 Part 5. And you need 2 of these, 2 different sizes, 2 different holes to cover reasonable pressure drops or minute ventilation and 135 liters, which is the range that ISO tests. And you put it in the mouth opening here together with the different head forms. ISO, same size trachea for all. It's the head form. They come in 5 sizes and fit almost everybody. And we didn't really know what the value would be, the worker breathing average pressure. So we sent the same trachea around to various pressure labs on 2 continents, and we got a consensus from those numbers. That became the standard. How do you make a decision on whether a particular device is acceptable or not? So you can plot the volume average pressure, so mean pressure, for different minute ventilations. And the red markers here are the ISO limits based on inspiratory systems only. And these are then based on people's tolerance. So if you put in your test data, you can then see that the particular device was acceptable up to about here, but would have too much resistance over 65. And whether 65 would be acceptable or not depends on statistical analysis. I think you can. How do you calculate the total load? I mentioned the average pressure, the offset pressure, the starting pressure, and the elastance. We also have from empirical testing, we know that the maximum elastance is a certain value and the pressure offset is a certain value as well. So you can take an example. The inspirator work was 0.4 kilopascal and the expiratory was 0.3, and the elastance somewhat different. And the inspiratory work was higher than the expiratory, so that became the limiting factor. And it was 0.4, and you allowed 0.9 from the previous graph. So that was 45% of its maximum value. And the elastance was 1 centimeter per liter, and you can have 10 to 15. So worst case, it was 10% of its value. Pressure offset was 3 centimeters, and you allowed 10. So that was 30%. You add up 45, 10, and 30, you end up with 85%. So the whole load, overall load, would have meant it was acceptable. And we're coming in towards the end here. The CO2 is sort of a hidden load. You can't see it, you can't taste it. So during an exhalation, CO2 can be trapped in an RPD. If you think of a snorkel or a piece of pipe, when you exhale, you fill it with CO2-rich gas. And as soon as you start to inhale again, you get a CO2-rich gas. And the volume of that is what you call dead space. So to get the same amount of fresh gas, you have to breathe more. And this increased gas flow then magnifies the effects of the other respiratory loads. You thought you needed, say, 50 liters a minute. Now you have a dead space. You may need 60 or 70 liters a minute to the same amount of fresh air dilute the CO2 you're producing. And how much is acceptable? The lower table here is from one of the ISO documents, and NIOSH has exactly the same limits for use without RPD. And the key word here is without imposed breathing resistance. And you can tolerate high CO2 levels for quite a long time. Because here you can take 2.5% forever, or unknown at least. And all that happens really is that you breathe more. And 5%, you can breathe up to 8 hours. But, and this is at rest. During an extremely high work rate, you can take 2.5% for quite a long time. Hours is a very long time. But if you now have some sort of apparatus in your way, and if the words you're looking for, it would be here against imposed breathing resistance of a level commonly seen in RPDs. And here, you can only take 2.5% at rest. If you don't have it, you could take 2.5% at an extremely high work rate. And that is not the case. And that is new information in the last 5 or so years. What happens when you have breathing resistance? And when you breathe high levels of oxygen, say 100%, it turns off the body's fast sensing. The body has really two ways of sensing CO2. One is fast sensors in the arteries leading to the brain. The other is in the brain itself, but it's a much slower sensor. And high oxygen levels turn off the fast ones. And if you may remember from control of breathing, control of any control system, if you have slow sensors, you don't get as good control of anything as if you have fast. And breathing 100% too has been shown to increase CO2 levels in the body in people. So to finish up, the body has to remove the CO2 it produces. That is the anyway. And RPD can be very useful. You can go and buy groceries nowadays, but it makes it harder. And there are ways to determine how much harder it gets. And such measurements can be compared to tolerable levels based on people's tolerance. And certification agencies and test houses make such determinations and to see if it is acceptable for use outside. Yeah. Thank you. And on the lower right there, you have my email address if you have any questions or if you want a copy of that report. I'm happy to send.
So thank you for that insight, Dan. Really, really useful and insightful. Just a question from my side to kick things off. With the ISO head form, do you see any variation in results from changing angular and diameter of the breathing tube itself? Does that affect these type of results significantly? Because one of the arguments within the ISO community has been kind of reproducibility of results across different test houses. So I just welcome your thoughts on that kind of geometric variation of head forms, or is it does it have to be a specific type?
Well, when we wrote that, we wrote it had to be a certain bending radius and a large pipe, so that the most of the resistance is in the orifice. We now know that there are other companies that have built it at a different bending radius. So actually, I'm part of a working group within the test methods group that over the summer ran tests where I built essentially took a PVC pipe, had it at 45 degrees, bent it and glued it together again. So it's an absolute sharp 90 degrees, nothing gradual in it at all. It's just being an L, and built one like from plain PVC. I built something out of what you can buy as drain pipe for almost no money at all, and ran all these tests at all of minute ventilations with both orifices. And the pipe bending radius has absolutely nothing to do with anything. There is no difference. I would not necessarily go to a smaller diameter. We have specified 32 millimeters as a pipe diameter. I would not really want to see a smaller pipe than that, because if you're going to move 135 liters a minute through that with a peak flow of 400 liters a minute, you should have a large pipe to maintain the right flow waveform generated by the breathing machine simulator. But the bending radius doesn't matter, and we are working on finishing up new revised drawings for that. Supposed to have a phone conference this Monday, but we postponed it because of Queen Elizabeth's funeral.
Okay, thank you, Dan. That was it was a very insightful talk around kind of CO2 buildup, and I think it's definitely confirmed my view of not everybody breathes at 40 liters a minute, especially when they're not exercising, that people under duress breathe at different rates, and often the standards can be at odds to kind of how it is in the real world. So thank you for that excellent talk. I think people are still digesting that, Dan. So if you're happy to stay until the end, we'll pick up further questions at Q&A. But in the meantime, thank you very much for what was an excellent talk.
Thank you very much. Back to you. I'll off my camera now. seen enough of my hand waving.
Thank you. So just moving quickly on to our next talk. So we've talked about why humans breathe and the challenges of standardization around that. Now we're actually going to get down to the fundamentals of filtering contamination. So it's a great, I'll change it into the right setting. It's a great pleasure to introduce Dr. Eva Dixon, who is both a defense scientist for many, many years at the Royal Military College of Canada. And it's been a great honor and a pleasure to work with Eva over the past few years in her role as, she's only just stepped down, but she has been the president of ISRP for the last few years. And Eva's going to give a presentation on the fundamentals of filtering RPDs. I'm not going to talk too much about Eva's background because I would literally be here all day. She's been an eminent scientist for more than 30 years, involved in defense, respiratory protection, and she's worked with many, many international agencies, NATO and ISO, just to mention but a few. And with that, Eva, I will pass the floor over to you.
Well, thank you kindly for that introduction, Dave, and thanks very much for inviting me. So let me just get things going here. And let me know if you are seeing this in the right mode.
Yep, we've got that.
Okay, great, thank you. Sorry, I just have to tidy my screen up so I can see it too. All right, thank you very much. I'm here today to talk to you about the fundamentals of filtering RPDs, which are both powered and non-powered. So I will be reviewing a lot of the sort of real basics of respiratory protection to make sure we're all on the same page before we start addressing some of the details. And some of what I talk about will refer back to some of the information that Dan presented as well. Thank you, Dan. I will be talking about common air purifying respirator design features and components, some of the styles and the relevant applications, some of their failure modes, and how to prevent them by selecting or using a respirator properly, and then the EN and ISO standard descriptions of respirators corresponding to the styles that I talked about earlier. So the first point, which should be pretty obvious to everyone here, is why do we need respiratory protection? So obviously we want to protect the respiratory tract, and sometimes we're looking also at the eyes and the face from hazards that might cause illness or death. And what types of things we're trying to protect against? Things like hazardous chemicals, infectious biologicals, with which we're all far too familiar these days, and radiological materials are the common hazards. And we should remember that respiratory hazards are primarily carried by or present in air. So it's always getting at your respiratory tract through the air. There's various possible physical forms, but essentially they all come down to two forms, which are vapors and gases that are single molecules of a substance and are very tiny. And the alternate is liquid or solid particulate matter, which is quite a bit larger. And it's some form of aggregated matter that is described by a whole variety of terms, such as aerosols, dust, sprays, mists, and fumes. It could be liquid. It could be water with dissolved or suspended solids. It could be live biologicals in some form of matrix, or it could be a dry solid. It's also worthy of note that occasionally bulk liquid hazards can become respiratory hazards if they're in direct contact with the respirator. In a few cases, that can happen. So what are some of the common design features and components in a respirator? So first, before we talk about that, we just need to talk about the mechanisms by which air purification-based protection can happen. So the first mechanism with which I'm sure you're all familiar is filtration. And that means that the hazard is being removed from the breathing air as it flows through some sort of a filter. And I'll talk about what those filtration mechanisms are in a bit. The second mechanism is reactive, and that means that something usually in the filtering medium has been added to react with or neutralize the hazard as it comes in contact with the filter, instead of simply removing it. Now, the respirator facepiece can also act as a barrier or other components of the respirator, so they're trying to stop the hazard from reaching the inside of the respirator by any other route than coming in through the breathing airstream. And then finally, we have clean air flow and overpressure. And the function of those approaches is to both flush out the respirator and attempt to drive leakage outwards. And we'll talk a little more about leakage coming up as well. So let's talk about the common components of an air purifying or filtering respirator. And I will emphasize not all these components are present in every style, but this covers most of the components you'll find. So first of all, there's some type of face piece, or this could be a head piece instead over the entire head. If it's a face piece, it will have some sort of a harness to hold it tight to the face. Then on the inhalation side, we will typically have a particulate filter followed by an absorbent filter if both are present. Adsorbent filter, and the particulate filter removes particles. The absorbent filter typically removes chemicals. In the case of an assisted device, we can also have a blower that's behind those filters. Then we might have some form of inlet valve, and the function of that is to keep exhalation air from moving backwards through the filter, because that can sometimes affect filter properties. And on the exhalation side, we can have an outlet valve, which is, again, intended to keep air from coming in on the inhalation, but it can reduce the breathing resistance if it's present, rather than breathing through a larger filter device. So what do some of these things look like? We're talking first about filters. They come by many different names. They can be called canisters, cartridges, air purifying elements, and in the case of filtering facepiece devices, with which you should all now be familiar because of COVID, the entire device in large part can be a filter with just an added harness and possibly an exhalation valve. We can have an attached blower. So the blower would also be something that appears in a device that might be called a powered air device or an assisted air device. Those blowers can have a lot of different shapes. They will all somehow take the filters that are going to filter the air before it goes through the blower with a hose that will attach typically to the facepiece, although there are some styles of blower devices that can be attached directly to the facepiece as well. You can have a headpiece, which is worn over on the head. So this headpiece might be loose fitting in the case of a hood or a helmet style device, or tight fitting in the form of some sort of half or full facepiece. So usually the function of the headpiece is to act as some sort of a barrier with the filters attached to it, except in the case of the filtering facepiece where it isn't really a barrier, it's just a filter. And the headpiece directs and contains the clean air so that it is moving in the right direction, inward on inhalation and outward on exhalation in most cases. It can also be used to hold various other components of protection that you might also need as part of the device. So what is particulate matter? That's one of our big hazards for which we need particulate filtration. So one of the first important points to remember is that for the purposes of respiratory protection, 99% of the time, a particle is a particle. It doesn't matter whether it's living or not, whether it's liquid or solid. There are characteristics of particles that can affect how well they're filtered. And those characteristics may depend on the type of material the particulate is made of, but they're kind of universal to particle physics and really don't have anything to do with other characteristics that we tend to think matter, like whether it's a liquid or a solid or a live. Those characteristics that can affect filtration are also vary over time. So the result that one might get immediately after particles are released won't necessarily be the same as later on. And this graph here just shows the various types of materials that can be considered particles, and many of which would be some form of respiratory hazard. And noticing that this is a log scale in terms of size, you can see that gaseous contaminants, which are not particles, that are in the lower left-hand corner there, are much smaller and hence have to be removed by different approaches than all the particulate matter that appears up in the top right portion here. So there are a number of processes that can remove these particles from the airstream, and they're all wrapped up in filtration. So filtration for particles is a concept that usually involves some sort of a fibrous mat. I've just shown an electron micrograph of one example of what a fibrous mat could look like on the left-hand side. Those fibrous mats can be made of different types of materials, but essentially they're all designed to provide a relatively low resistance to the breathing air while at the same time performing filtration by the mechanisms that are on the right. So those mechanisms include things like inertial impaction. That's important for larger particles, which essentially can't follow the airstream. So you can see the airstream will go around this fiber in the fiber mat and continue onwards, but very heavy particles can't follow the airstream and simply hit the fiber. Interception is a sort of an intermediate effect where the particle that follows the airstream still comes into contact with the fiber because it's near enough to the fiber in order to become attached to it. This effect also happens in diffusion, except this is for very small particles that tend to follow their own path more than following the airstream. And so even when the airstream has gone past, sometimes a very small particle can diffuse and come in contact with the fiber regardless. And the last significant mechanism is what we call electrostatic attraction. And it has to do with the fact that a fiber can actually have a charge on its surface, and many particles will actually have a net charge on their surface as well, having to do both with their makeup and how the particles were generated in the first place. And that electrostatic attraction can take the particle out of the airstream and attach it to the fiber as well. The last mechanism, which doesn't tend to be as significant in respiratory protection, is settling, which is just large particles falling out of the air. So another important point is particle filtration efficiency by particle size. And this becomes quite relevant when you start talking about the way that standards work to describe how protective a filter is. So the major mechanisms that have a significant effect by particle size have to do with diffusion. So you can see diffusion is very efficient, 100% efficient, once you get to very small particle sizes. So those particles will be taken out by fibers very effectively. Interception, which is the one where the particle cannot follow the airstream around the fiber, becomes really effective as particles get larger. And similarly, impaction is a similar sort of effect, but it only starts to come into play at a slightly larger particle size, but eventually, again, is responsible for nearly 100% filtration. And of course, these filtration efficiencies depend on the flow rate that you're using to measure and a few other things. But so just relatively speaking, you can kind of understand. So it's important to recognize that particularly in the presence of large particles, you're getting extremely effective filtration by almost any kind of filtration device out there. So when a number is reported for a filtration device of how effective it is, that number is usually reported at the most penetrating particle size. And so that particle size can differ, again, slightly depending on the composition of the filter, but it's going to be somewhere in this region of sub 1 micrometer in size, and possibly occasionally even below 0.1, but commonly it's around 0.2 or 0.3. And so you can see that that curve, which is the sum of all the other curves, dips significantly somewhere in the middle. And that's where this highest efficiency value is, or sorry, rather lowest efficiency value is, which is the value that's used to report filtration efficiency. So that number might seem low in some cases, and it might worry you a bit, but remember that in fact, the measurements being done at that very low, the most penetrating particle size, and there's a lot of other particle sizes that are in fact being filtered much more efficiently. So what about gases and vapors? By far the most common filtration medium that's used in filters to remove gases and vapors is activated carbon. And activated carbon, it looks like carbon, which many of you would have seen. It's been treated in a particular way to make sure that it has a very high surface area and it's very porous to gases. It's produced in various grain sizes. If it's kind of a granular material, and those pack differently, so you can use different grain sizes to get different surface and flow rate characteristics in a filter. Sometimes it could also be fibers, which have a very high surface area as well. And regardless of its particular form, it's intended to remove, in particular, larger and high boiling molecules by a process of adsorption, or what's also called physisorption. And if it's impregnated, and I'll talk about what that is in a second, it will remove targeted smaller or low boiling molecules by chemisorption. So what's the mechanics of that? In the bottom diagram, you can see we've got something that looks a bit like a crudely drawn surface of what activated carbon might look like. And you've got different sizes of gas vapor molecules approaching that activated carbon. So you can see the activated carbon has pores in it. And what can happen is that the molecules can enter those pores, and then because they're in contact with a lot of different groups on the surface of the carbon, because the carbon will also have other chemical groups that may be attractive to a molecule, larger molecules can simply become stuck in those pores, attracted to the surface by these van der Waals forces and occasionally by electrostatic forces. But smaller molecules, very small molecules, just have too high a vapor pressure to actually get stuck that way. They don't come in contact with as much of the surface, and they don't tend to have as many points of attraction. So in order to get those to attach, you have to add these molecules called impregnants to the surface, and these are simply drawn by these little hexagons in this diagram. And those impregnants will have some sort of a chemically reactive material in them, often things like metals or bases. And those chemically reactive materials will actually attract these much smaller molecules and get them attached to the surface effectively by chemical reaction instead of just by being sticky. And obviously anything that's a chemical reaction has to be kind of specific. So that means that these impregnants don't necessarily remove every small chemical that comes along. They have to be designed to work with particular classes of chemicals. So that basic background is what you need in order to understand general styles and applications of how air purifying respirators work. Everything else is just an application with understanding how these different mechanics of removal of chemicals work. So the simplest version of an air purifying respirator, with which we're all horribly familiar at the moment, is a filtering face piece. And that's typically a half face, or sometimes called a half mask, and the entire facial covering filters particles out of the incoming air. And there are various styles of these. They can be in the shape of a cup, which has a sort of a firm sealing surface to the face. They can be in the form of something that folds, which doesn't have quite as solid a sealing surface to the face. Depending on what jurisdiction you're in, the style of the harness may need to be different in order for it to be called a respirator. It may have an exhalation valve, which means that the breathing resistance on the exhalation side can be reduced due to that presence. And added in, it may have specified additional protection. For example, for a surgical medical application, there may be requirements for fire retardancy or jet and spray repellency that are intended to deal with things like a blood spurt during surgery. And here's some example terms from standards. In the EN standards, these are called FFP1 to 3, depending on the efficiency. In case of NIOSH, they might be an N95 or an N99. Coming from China, they might be a KN95. They all have different requirements slightly, and certainly we can talk about that later. Examples of where you might want to use filtering face pieces are they're often used as some form of dust mask, and they're often used as protection against infectious hazards. And of course, there are other applications as well. So if you want to add a little extra protection due to a good face seal without changing the amount of the face that you're covering, you can move up to a half-face elastomeric mask. And the reason these are slightly more protective is because they have a better conformal seal to the face than a filtering face piece does, which means you get a reduction in face seal leakage because of that nice, soft polymeric material that's making that seal against your face. It uses filters to purify the air, in this case, instead of the entire face piece. And this bumps up the options you have for the type of protection it's providing, because you can get cartridges, canisters, filters that remove gas and vapors or particulate or combined to do both. And it's common that there might be 2 of these filters on the device, which significantly reduces the breathing resistance, because now you've got twice as much surface area to breathe through. Another example term that's used for these is elastomeric half-mask respirator, which nicely ambiguously includes the word mask with respirator. And again, what's a common use for these types of things? Again, they can be used as dust masks. They can be used to remove paint vapors, and again, for infectious materials. Now, the full face elastomeric negative pressure respirator also uses filters. Here's a couple of examples of what something like that might look like. And now you've incorporated both a barrier and a face seal, and that face seal now is over the entire face instead of just around the nose. And that means you're getting eye and skin protection on your face. Eye protection is usually the most important reason. That eye protection might be important not because you need protection against the specific respiratory hazards from the material, but you might need to be providing protection against some sort of other physical factors that are at play when you're doing the work that you need to do. Usually in this case, the filters would be either straight chemical filters or combined filtration. It's less common for them to be particulate filters, but they can be. The material they're made out of is often silicone rubber, which is very soft and conformal to get a good seal. When you're trying to get a lot of protection, and now you're talking about protection against highly hazardous chemicals, you may need to use something like a halogenated butyl rubber in order to protect against chemical permeation. And I'll talk a bit more about what that is later. So a powered air purifying respirator, which in Europe can be called an assisted style of respiratory protection, you can get any type of headpiece that you combine with high airflow provided by a blower. And high airflow by itself is already good. In some cases, when it's a tight-fitting style, it has the potential to also deliver overpressure, which is even better. And it's suitable for higher hazards and also for reduced breathing resistance when it's tight-fitting in particular. Hoods and helmets, they're very useful, for example, for bearded individuals who can't get a tight seal. And because you no longer have a tight seal to the face, you need that extra supplied air from some source in order to flush the respiratory cavity, face cavity out so that the breathing air is clean. This also can potentially lower the burden to an individual, at least in terms of breathing resistance. Obviously, you have to carry the blower, which can be another factor. And finally, the last type I'd like to mention is what's called a self-rescue or an escape hood. These can be very simple. They're intended for emergency use, for exiting an area that has suddenly become hazardous. The big advantage of this style is that they don't require the item to be fitted to you properly. So it is intended to just provide very short-term protection with some sort of air overpressure. And you can see this is actually not a filtering device, but I wanted to include it just because it's on the complete list of EN standards so that you can, in this example, it's not filtering, but there can be filtering versions as well. And it'll give short duration protection against specific hazards. So what are some of the features of high airflow and overpressure in terms of how they will help you protect? The first feature is that at the interface to your head or your face, you're getting typically outwards flow, so that much of the time, materials that are outside the head or the face are not able to get in through leaks in the seal or in the respirator. And if you are trying to create overpressure, that good seal in a well-sealing version assists in creating overpressure, which does an even better job of assuring that if there is a leak, the flow will be outwards when it happens. And leaks can be transient. They can be created by movements of a respirator on your face, for example, that cause a leak to form for a short period of time, and then it will seal again. And so you want the air to go outwards if that happens. Your exhalation valve can help maintain the overpressure and also potentially make breathing easier, depending on whether you have some sort of a compensation valve in there. Compensates for the higher pressure that you need from that exhalation valve, which is, again, trying to keep flow outwards only and possibly help in creating overpressure. The entire system is kept clean by that high flow, which flushes out contaminants that get in. And depending on the style, a loose-fitting respirator doesn't do nearly as good a job of keeping contaminants out when you breathe in, because you can often create inward leakage by doing that, create negative pressure. So what you want is a high enough flow that's just going to keep those contaminants flowing outwards, even if they do manage to get in. So it's flushing them out. It reduces the breathing resistance in general, and it also reduces the buildup of moisture and carbon dioxide, which, as we know, is also beneficial for comfort and increasing the tolerance time of respirator. There's also the case of the difference between a continuous flow device and a demand device. Most powered air systems are for filtering our continuous flow, which means you just turn them on and the flow goes. There are a few that actually have adjustable flow so that you can set it depending on your work rate, and that helps with extending the battery life of the blower in particular. There are a few such devices that are demand devices. That means they only supply air as it's needed in order to maintain the flow and the pressure depending on breathing cycle. So what are the most common failure modes and how can you prevent them? So the first failure mode is that these devices typically have some sort of a barrier in them to keep things out, independent of the airstream. So you're looking for something that has tight seals between the various components of the respirator. You're looking, and that tight seal may be to the face as well. You're looking for an air impermeable material, so it's going to stop most particulates from penetrating through holes, cracks that you don't want it to go through. You want to avoid contact with bulk liquid hazard, and you, in some cases, might need to select chemically impermeable materials for that barrier. And so just to differentiate a little bit, the two mechanisms I'm talking about are penetration and permeation. So in the case of penetration, you have anything from a molecule to a particle that's somehow getting through holes in your material, or whatever those holes have been created by. In the case of permeation, there aren't any holes, but something has come in contact with the material and actually dissolved into it. Usually that would be something like a liquid drop. And then once it's dissolved into the material, it can work its way through and come out the other side. And typically that's a matter of hours before that will happen, although depending on the thickness of the material, it can happen more quickly. So in order to reduce that leakage around the face seal, you want to buy something that has a very nice conformable material, or a good seal design to your face, or a very carefully shaped and sized sealing surface in general. So for example, a cup-shaped filtering face piece respirator will generally provide a better seal to the face if it's well designed than any type of folding filtering face piece, which just doesn't have the same ability to make that seal to your face. And one of the consequences of a good seal is usually you're going to give up a bit on comfort. So most people would say, for example, that a folding face piece respirator, filtering face piece respirator, is more comfortable than a cup shape. So you're trading off comfort for seal, typically in that case, although obviously there's always exceptions with good design. You want to hold the respirator to the face with effective straps or harness to make sure that it doesn't move around. And factors that can make the leakage at the face seal worse can be things like a weight imbalance on the respirator, sweat on your face. So anything that keeps you from sweating will definitely improve your seal overall for the most part. And activity in general, once you start to get sweaty, will also cause dislodging more easily. And various types of interferences that might prevent a good seal. So facial hair, jewelry, and other types of equipment that might come in contact with your respirator. For example, if you're wearing a helmet, that helmet can sometimes ride on the face piece, and the fact that the helmet might bounce on the face piece can actually cause the face piece to come off your face. So consideration of the other equipment that you're wearing at the same time is also important. And of course, providing that high airflow or overpressure will also reduce the likelihood of leakage around that face seal. So what about proper fit? Fit factor and protection factor are two ways that we describe what proper fit is, and both of them reflect the same thing in terms of just the mathematical expression, which is the factor of improvement of protection you get when wearing the respirator. So you compare what's outside to what's inside. And the other term that's often used in standards is inward leakage, which is just the inverse, the concentration inside divided by the concentration outside. So you can measure the protection that somebody gets when they're wearing a respirator. And this is someone in my laboratory having a quantitative fit test done in order to measure their fit factor. So what's the point of a fit factor? A fit factor tells you whether the respirator actually is the right size for your face. It doesn't necessarily reflect how well it will do in practice. So those are two important distinctions. So when you're doing a fit factor test, you're trying to select the best option from what you have in front of you to fit your face. If you have more sizes in a particular respirator or more available models of respirator to pick from, you're more likely to get a size that fits for your entire group. It obviously means the fitting process takes longer, and this is why some organizations choose to do differently. And not all jurisdictions require a fit test in order for a respirator to be issued to an individual. So it's important to understand what your item can actually deliver in that context. A protection factor measurement, on the other hand, is one in which you look at all the sources of leakage and not just whether something fits to your face properly, and typically may be measured more realistically. in using a procedure like a simulated workplace protection factor measurement or a workplace protection factor measurement, which is a real measurement in the workplace, to determine whether a particular solution is going to work in practice. So then you have individuals doing realistic activities with wearing their full equipment, and you try and understand whether the protection is being maintained in the workplace. So finally, you have an assigned protection factor, which is the minimum workplace protection factor that you'll get from a particular style of respirator when it's properly fitted and worn in use. And that assigned protection factor, which is a sort of a combination of a practical number and a theoretical number, because it's a kind of a theoretical worst case, not completely, but for most people, that assigned protection factor can be different by jurisdiction. So particularly if you look in Europe, every jurisdiction might have different values for what that assigned protection factor of a particular style of respirator is. And then when you're doing a risk assessment during your selection, you're looking to define what the required assigned protection factor is in order to get the best protection from a device. I'm going to give you the Canadian assigned protection factors because that's what I'm most familiar with, being from Canada. But of course, in your jurisdiction, you'll have to figure out what it is. So in the CSA standard that was mentioned by Dan, you can see that air purifying devices fall into all these bottom categories with assigned protection factors starting as high as 1,000 for items that have airline or face piece, pressure demand or continuous flow, half face piece, or, oh, sorry, that's the atmospheric. Reading the wrong side. Powered air purifying full face piece, powered air purifying helmet or hood that has had an SWPF study that shows that it can achieve this value, and various other options with much lower values. So what are the sources of ingress in the breathing airstream? First of all, you want to provide highly filtering materials if you want to keep air out of that, or keep the hazard out of that breathing airstream. And you want to look at the percentage filtration as an indicator for particulates, and you want to look at capacity for gases and vapors. So gases and vapors typically get removed almost completely initially until the capacity is used up, and then they start to break through. For particulates, the percentage filtration tends to be roughly constant the entire time you use the device. But it's also important to remember that that higher filtration efficiency or capacity increases the work of breathing. You've always done something to change the surface of the system that you're breathing through. In most cases, that's going to put more material between you and the air. And the downside of that, of course, aside from the fact that you've increased the work of breathing, is that it can also drive inward leakage of the face seal, because typically, as you start to breathe harder, when you become active, you're going to create that greater negative pressure during breathing. And that's going to try and force leakage from different locations. And so if it can't come through the filter, it's going to try and come through somewhere else. So what other considerations do you have for selection? Weight and bulk. You want to try and keep the components as close as possible to your body to prevent both weight imbalance, which is going to pull the respirator off your face, and snagging of various components during work. It generally reduces the physical burden to keep the weight and bulk down, and which is also going to reduce the physiological burden that's imposed as a result. Again, breathing resistance, we've mentioned it many times, and Dan did too. You want to minimize the work of breathing, particularly at high work rates. You'd like to see a demonstrated ability to fit the desired user population. And again, this is very sporadically applied currently, but there can be fit test anthropometric panels involved in the certification of a respirator, in which the respirator has to be tested with different sizes of people. And so you look for how many, what percentage of your population might be fitted by having this particular device in whatever size options are available. And again, in order to fit your population, you may need to have more than one model that fits differently. And it's important what your population is as well, because a model that has been designed to fit a Chinese population is not necessarily going to fit a European population well. Fogging is also a consideration. That can be reduced by treating the visor or eyepieces of the respirator with some sort of a repellent material, and also by passing the dried air over the visor and the eyepieces as part of the way the airflow works in the respirator if possible. Carbon dioxide and moisture buildup are generally prevented by the presence of a nose cup in a respirator and the design of the exhalation valve. Vision, you want a good field of view, obviously. You want to look and see if something offers corrective eyewear that obviously should not break the seal of the respirator, so something that can be mounted inside a full face piece if you have a full face piece respirator. Head and eye protection are often very important for the tasks that are going to be performed, so you can have things like helmets or tinted visors against hazards like welding or sun exposure or lasers. Single versus multiple use is very important. So if you're going to have multiple use, you need to be concerned about the ease of cleaning or sterilization for reuse. You have to be concerned about the waste and the consumption rate in either case to make sure you manage that properly. And you want to be concerned about the durability and repairability if something is multiple use, and whether or not you need a protective carrier for it, and whether something is available. And one really obvious one is the nature and concentration of the hazard you're trying to remove. So some chemicals are difficult to remove or are present at really high concentration. And in that case, you may be required to move to supply breathable gas, if so. Otherwise, you have options within your standardized respiratory protection. So in terms of selection, there's many design features that you want to consider when you're selecting. And understanding the standard that you're trying to work with and how its requirements are applied can be very helpful, and they really are not all the same. It's really important to get training in the correct use of the device so that performance is maintained, and if possible, a proper fit test when issuing it. And you've got the availability of lots of different types of selection and use guidance by jurisdiction and in various internationally available standards to help you with that process. So the last area that I would like to touch on just very quickly is the EN and ISO standard descriptions of respirators, so that you've kind of got the understanding of the language and the standards that you would be working with in selection. So these are the EN standards. I'll start with them because this is what most people are going to be using at the moment. So this is a complete list of all the EN standards that address respiratory protection. You've got the standards that talk about the full, half, or quarter face pieces or even mouthpiece assemblies, and the corresponding filters that might go with them. And you can see there's different standards for different types of filters depending on what they are intended to remove and whether there's a breathing hose involved. We have a separate standard for filtering face pieces, and in this case, they're broken down by different styles with whether they have inhalation valves, exhalation valves, etc. We have the self-rescuers, which can be filtering devices with a hood or filter self-rescuers. And then we have the assisted air devices, which are powered filtering devices with a helmet or a hood, or powered filtering devices with a full face mask, half mask, or quarter mask. So those are all the European standards that apply. Obviously, it would take much longer than we have here to go through all those standards in any detail. But I would just like to point out, and as Dan mentioned, there's now ISO standards for respiratory protection that have recently just been published in their entirety. And there are not any devices yet that are approved to these standards. So right now, this is more of a basic understanding so that if and when devices do become available that fit that meet the standard, you'll understand what the difference is between that and the EN standard. But the ISO standard is really performance-based. You can see that the EN standard was much more based, at least partly, on the style of the respirator. ISO standards are based on performance parameters. And so they can be described by various terms, such as protection class, in which case you're looking for a variation in inward leakage, which, as I said, is the inverse of the protection factor. And so relatively high inward leakage up to 20% and down to much lower values of 0.001%. And that's protection class. We have the work rate class that talks about what work rate a device is intended to be used at. And that goes back to Dan's points in terms of what sort of work of breathing a device might be expected to deliver. So the respiratory interface class describes the way that the respirator interfaces with your body. And so they're all covered by these letters that describe where the respirator sits or how it works with your body and whether it's tight fitting or loose fitting. And you can see that the respiratory interface includes everything up to the body. So the respirator can be incorporated into a full body device. And then separately, we've got the filter classification. We've got this option of, first of all, particle filter efficiency. Again, those numbers you may be familiar with in terms of the range between 80% and 99.99%. And then you have the filter classification by the type of thing that it removes in terms of gases. So you can have either sort of more general gas filters that look at things like nitrous oxides, organic gases, basic gases, etc. Or you can have specific gas filters and combinations of specific gas filters and other types. And then finally, the filters can be classified by work rate, and the work rate description was given on the previous slide. And that is everything that I was hoping to present today. So I will be happy to take questions once Dave has us all answering questions at the end, and my email is given here in case you have any questions you'd like to reach out with.
There's nothing at the moment either in the chat other than from Louise, who unfortunately had to leave, but she just wanted to thank you for an excellent presentation, which I thought it was. There's often discussion around which is, with assigned protection factors aside, from a filtration perspective purely, there's often a discussion around the advantages and disadvantages of APR versus PAPR. And I'm thinking kind of in the CBRN world, because there's many operators that talk about a PAPR is essentially you're pre-concentrating because you're operating at that higher rate if the filter fails. So where if you see where I'm coming from, the fact that you're using that. So in terms of within your day role, when you're kind of factoring this testing in, is that the kind of thing that you look at in terms of whether to choose APR versus PAPR? I'm just trying to give the audience a feel between kind of that selection choice of when to look at PAPR versus APR.
Well, one of the biggest factors that we have found, there's two issues here. The first one has to do with the general selection of an air purifying device versus a supplied air device. And we actually know lots of organizations who will have chosen some sort of a device that has both a supplied air option and an air purified option built in together, with the intention that they would switch from one to the other when necessary. The biggest problem with that approach is knowing when to switch. And if you ask any organization how they would know when to switch, they would just answer you with, well, it just depends on the situation. But in fact, that's not an answer. And most of them actually would not know when to switch. So it's a very seat of the pants discussion. So I would say if you are concerned with the ability of your filter to remove the hazard, for whatever reason, you're always going to have some way of knowing when it's not working and knowing whether you have to leave or switch. And that's the biggest gap, honestly. So it's not so much whether your filter is going to last as did you know it was ever working in the first place? Or the second part of the question has to do with the difference between powered air and air purifying. And in our case, it's clear that many of the options you have for protection out there haven't really been evaluated in realistic circumstances. And that when you combine the respirator with some sort of additional body protection and high levels of activity and sweating, that the level of protection that you're getting from an air purifying device without assisted air is considerably lower and much lower than you might hope.
Yep.
And that in a well-designed device, when you've added the assisted air, powered air system, you actually are bringing that protection back up to where you would hope it was. And it does overcome a lot of those issues of practical use. So it actually does have all the benefits one would hope to add that powered air back in. And the air purifying systems really have difficulty maintaining the required level of protection. Again, that's a little more in the civilian case. You'll find that in the military case, a lot of the equipment is better integrated. It tends to be a little more air permeable instead of air impermeable. That means the sweating is less, the integration's a little better. So the military actually tends to do better with air purifying respirators because of that. So I don't know if that answers your question.
No, it does. It's kind of, and again, it's which application are you talking about? And it's often a challenge because people are trying to stovepipe a product into a particular area rather than kind of look at the hazards and what you've got to mitigate. So no, that answered my question. So thank you. There are no further questions either at the moment. So in the interest of time, I'm just going to move on. So hopefully there'll be more questions at the end. So just to share my screen again. So for our last presentation for today it's a great pleasure to introduce Radha Krishnan from MSA, who's going to talk about self-contained breathing apparatus and connected safety systems and how they will solve your respiratory challenges. So Radha is based in the Middle East. It's a great pleasure that he's stayed online today. He's worked for MSA for a few years now, and he's their regional segment marketing manager for respiratory protection. But his expertise today is around breathing apparatus and in particular SCBA. So with that, Radha, I will open the floor to you.
Okay, hello everyone, and a warm welcome to all of you. I'm Radha Krishnan. Like Dave mentioned, I'm from the segment marketing team, currently based in Dubai. I'm so glad you have joined us today for our talk about basic respiratory protection, what, where, and why. I'm going to walk you through the SCBAs, various types of supplied air respirators, and how connected systems will help to resolve respiratory challenges. So let's get started. Next slide. Yeah, thank you. Of course, air purifying respirators. We heard it from other speakers today. I'm not going to look at that. But our focus today will be on supplied air respirators, popularly known as breathing apparatuses. This is completely independent from the ambient air. This is divided into autonomous, non-autonomous, and a combination as well. Our focus is on autonomous set, that is an SCBA. Next screen, please, Dave. Yes, you know what an SCBA is? It is a self-contained breathing apparatus set used to help safety officers, critical task members, firefighters breathe while working in an oxygen deficient atmosphere. An SCBA is short for self-contained breathing apparatus. At times, industry expert call CABA compressed air breathing apparatus, or simply the BA. The SCBA sets rely on an independent source of compressed breathable air through an attached cylinder, air cylinder. By the way, an oxygen deficient atmosphere is also known as IDLH, or immediately dangerous to life or health. SCBA also can be used in any unknown environment or an environment with unknown levels of contaminants. We are going to talk about the SCBAs and various types of supplied air respirators, and we are going to give you some practical tips for choosing the right SCBA, the respiratory protection that is crucial to the health and safety of working people. Plus, we are going to share how the connected safety system that can help save you cost, time, and money for a lot of customers. Next screen, please, Dave. Thank you. We all know the firefighters, safety officers, and emergency response personnel operate in a high-risk environment, and they need the best SCBAs. Here are just a few examples, typical applications where the users record supplied air respirators. In oil and gas industry, technical search and rescue, confined space, tank or reactor entry for cleaning and maintenance work, repair of gas lines, working in storage tanks or pipelines, working in truck or rail tank cars, working in tunnels, large machinery housings, working with liquids, gases, vapors, and particulate, hazmat response to toxic gas leaks such as chlorine or hydrogen sulfide or any unknown substances. Each of these is a unique application marked by a variety of known and unknown hazards. But we need an SCBA, right? What does it consist of? It's time to learn about it. Next slide, please, Dave. Yeah, as you see here in the screen, a standard SCBA will always consist of full face mask. That's the first one, full face mask, and a demand valve, and the back plate, a harness accommodating the high pressure reducer and the compressed air cylinder. The connection between the air cylinder and the face piece is the medium pressure line directly connected to the face mask with a demand valve or a regulator. People simply say LGDV or LDV, lung governed demand valve. All these components make an SCBA, but what the standard these are certified to? Let's talk about that in the next slide. Yeah, thank you. As a complete set, an SCBA is certified to EN 137, type 1 for industrial, type 2 for professional firefighting. However, each component is certified to different standards. For example, the full face mask, it's certified to EN 136, and similarly, the cylinder valve, EN 1441. When you look at the specific approvals for the SCBA, we do see the anti-static and CBRN, also MED, Marine Equipment Directive, simply people call that as a wheel mark. All this can be seen from the label that is affixed on the backplate of an SCBA. Though we call it as one SCBA standard certified to one specific standard, but all these components are certified to different standards. Okay. Yeah, next screen, please. Okay, now it's the time to look at the function of a breathing airflow. Once the SCBA air cylinder is turned on, the air flows in the system, and the SCBA user can be on air with the first inhalation. We call it as the first breath activation. The breath in air flows with minimum resistance, making breathing through the mask very comfortable. Exhaled air follows the route to the outside via the exhalation valve in the face piece. The normal breathing in and out minimizes any fogging that could develop inside the mask and the voice transmission through the component called speech diaphragm. Breathable air inside the air cylinder is compressed up to 200 or 300 bar, subject to your cylinder type. Many customers use 200 bar, or some people use 300 bar. Depends on the duration one prefers for the SCBA. This is high pressure. Obviously, this is regulated down and done in 2 stages. The first stage of air pressure reduction is performed by the pressure reducer bringing down the air pressure down to approximately 7 bar. And in the second stage, we call it as a second stage regulator or the demand valve that further drives it down to 3.5 millibar, from the bar to the millibar. And then once the breathing through the SCBA starts, the full face mask is equipped with exhalation channels, allowing exhaled air to diffuse into the atmosphere or the ambience. That explains the complete airflow concept of an SCBA. This is common, this is standard, this is applicable for almost all SCBA sets. We don't see any difference for one manufacturer or to the other manufacturer. This is what the airflow for all SCBAs in the market here. Next screen, please. Yeah. Okay, it is essential for us to make the most informed and ultimately best decision about supplied air respirators. In the market, there are different types of SCBA sets available, starting from customers can select for the compliance or the wall hanger set, the most economical, or some of the sets available readily assembled as a kit for ready-to-use conditions. And some customers prefer to have a customized to suit based on their requirements and applications at the site. Of course, this is entirely dependent on the budget and the required feature as well, such as some people prefer analog pressure gauge or the digital type, etc. We will discuss about two imperatives here. That is one about the backplate harness options and then the pressure monitoring devices. Next screen, please, Dave. Oh yes, we mentioned about the features in an SCBA. One would think that most of the sets are certified to the specific standard, so we should get the best product, right? And no, it's not. To ensure the health and safety of firefighters, emergency responders, and industrial safety workers, we should look at having the comfortable and lightweight functional gear that offers the highest levels of personal protection. Not all workers have the same physique. So you should look at the feature to include the height adjustment. So the customers, that's what they need to look at that. So it can be adjusted to fit different body shapes and sizes. Similarly, think about the S-shaped shoulder harness, which prevents slippage and pressure points, keeping the weight more secure. That means the SCBA will not only be more comfortable, but they will also actually feel like users carrying less weight. SCBA sets are available in the market with the Thread Connect and Quick Connect options for this cylinder. When you have the threaded connection, so you need to take time to make it more suitable. But once you have that kind of a quick connect, what happens? Just one click, just press it, then that's it, done. So this is very handy for the easy change out of cylinders at the field. These are some of the features nice to have with the supplied air respirators for the safety and comfort during extended task at the field. Next screen, please. Dave, next one. Yeah, thank you. We talked about the backplate. Let us look at the selection of the best user interface for the pressure monitoring. Pressure gauges available from simple analog gauge to high-end digital for increased safety. It actually indicates the high pressure inside your breathing air cylinder. For ease of user visibility, the traffic light concept of green, yellow, and red is used to state the pressure status during use with body lights. This kind of pressure gauge is also available for the SCBA sets. Some of the pressure gauges available with LEDs to indicate the pressure status, and also it includes the motion alert that alerts against immobility that helps to increase safety awareness at the field. And some of the devices includes the integrated digital display for the ease of understanding, and also the optional telemetry to help remotely monitoring the pressure status from the workplace to the remote area. That brings the end of complete overview of what, when, and where on an SCBA. Part of the supplied air respirators, we now look at the escape, airline escape, and mobile trolley systems. Let's go to the next screen, please. Yeah. As you see here in the screen, some of the short-term escape sets usually meant for 5 minutes to 20 minutes of duration. We heard it from Dr. Eva, talking about the constant flow and also the regulated flow types. Typically, when we see here, this can be divided into two categories. One supplied with the hood in case of emergency, when the user just pull it on to down the hood, then airflow is activated and it is continuous and constant flow. Well, the cylinders in such kits are meant for only one-time use. So after each use, you need to refill prior to next use. That's how you use the short-term escape sets. And in the short-term escape sets, another variant is a full face mask. In this unit, the pressure can be controlled or regulated. It's a positive pressure type. And also a combination of both positive pressure and also the loose fitting hood integrated type is also available in the market. This is normally used by the customers having a facial hair, long beard. However, when the user is required to work on a long duration for specific tasks like spill control, tank cleaning, confined space entry, then the airline escape sets can be used together with an external air supply. We will talk about this more in the following slides. Next slide, please, Adim. Yeah, here we go. When and where to use such kind of airline trolley escape sets? Short-term escape sets can be hand carried to the field for personal use, but the mobile air trolley units to be placed at the nearest task area or the workplace and connected with an airline escape set. The most popular airline trolley units in the market usually accommodate the SCBA cylinders so that the customers can take the same SCBA cylinders and use it with the airline trolley unit, and also they can use it with the SCBA. So this is to ensure the optimum utilization of the cylinders in the field. A few trolley units available with the large air cylinders, typically that can provide breathable air source for up to 6 hours. As mentioned a while ago, we will look at the function of an airline escape set together with the airline sets now. Next slide, please. Yeah, here you see here in the screen, it's a typical application. You will see the mobile airline trolley unit, which accommodates the same SCBA cylinders. 6 liter to 9 liter, up to 9 liter capacity can be accommodated in this kind of a trolley units. So the construction goes like this. From the airline trolley unit, it is connected, the medium pressure air delivery hose is connected to the airline escape set. And then you got the automatic switchover valve, or simply people call it as ASV, automatic switchover valve. So the medium pressure air is connected to the automatic switchover valve device. Once it is the external air source is connected, then it pushes the spindle, and then what happens, you draw the air from external air source, that is here the airline trolley. In case the external air source is dropped down, or the cutoff, or the pressure drops down from the set level, then automatically the spindle goes down. Then the air is drawn from your the escape set. This is indicated by the whistle, warning whistle. So once the warning whistle activates, the user will be able to easily understand that the air is coming from the escape cylinder. Then again, the external air source is resumed, the external air supply resumed from your trolley. Say the one cylinder is completely emptied, then you need to change to the next cylinder. Then you get the pressure from your external source coming from your airline trolley. Then automatically it switch over to the external air source. Then your whistle stops. This way you can easily recognize, okay, the user can recognize such a way that, oh, I'm taking the air from the trolley, the whistle stops, and then I'm taking air from my existing bottle or the escape set, that means the whistle starts. So this way we can easily identify, the user can also identify that. Here what happens, this is very useful for the long duration for industrial applications. There are some other units available, like you can see on the right hand side, left hand side bottom. the breathing air filtration cum distribution units. Sometimes the people take the industrial air from the plant and they filter it to consume and then use it at the field. This kind of sets also available in the market for the customer use. Okay, now we are getting very close to the end of our session. Let's first talk about selecting the right SCBAs here. As you see here, I'm not going to deep dive into each topic, but one of the points we need to look at here is once we start by asking different questions and also looking at the answers to the question about contaminant type, concentration, hazard ratio, and the workplace condition risk assessment, we will be able to really get to the right SCBA or the supplied air respirators. The next one, Dave. With this in mind, I know, Dr. Yuva covered about the permeation. This is some of the, for the safety relevant point of conclusion, the nominal protection factor, which considers the inward leakage, must be considered during the selection of your SCBAs, but also we should consider the permeation. Some of the chemicals like hydrogen sulfide and phosgene can penetrate and pass through the silicon and the other materials used for the SCBA components. Even with the tight fitting face piece, you must, for the safety of your workers, consider the permeation too. Next slide, please, Dave. As you see in the screen, there are a number of factors to consider when sorting through the different SCBA models. Always ask key questions. Always key questions arise here. Because there is no one size fits all in the SCBA. So some of the key questions, as you see here in the screen, we need to really consider them as the key considerations to pick the right SCBA, also supplied air respirators. Let's move to the last topic, that is the connected safety systems, and discuss what, when, and where, and how it will resolve respiratory challenges. The connected safety platform is the expectations of our customers in the market. Here are just a few examples how the connected network system would benefit them and solve their respiratory challenges. With a connected network, a plant control room can receive the real-time information from the firefighter or safety officer in action. This real-time data is more than just SCBA air delivery status. It also ambient conditions. It delivers in real time questions like, oh, what are the gas concentrations near the firefighter or the workers in the operating area? With a connected network, the plant control room has the real-time essential information, allowing them to quickly plan for necessary support activities, including but not limited to rescue or recovery. Safety is the priority. Of course, the connected safety platform is what keeps firefighters, safety team, and emergency workers, rescue workers seamlessly linked. Connected systems can help increase visibility, improve efficiency, promote situational awareness, enable accountability. Well, when it comes to selecting an SCBA or supplied air respirators, we will always tell our customers that let the manufacturer's team help by working with you. Okay, moving to the last slide, Dave. I know we talked about a lot of things today, but for now, thank you, ISRP team, Dave, for providing the opportunity to us, and thank you for joining me. We look forward to seeing you again in a future session. Thank you, Dave.
Now, many thanks.
If anybody has any questions, you can always reach out to me on radha.krishnan@msasafety.com. Probably I can put my email on the chat box. You will be able to reach out to me for any questions on that. Thank you.
No, many thanks for that presentation, Reda. I thought it was excellent. It's great to see a mixture of kind of new telecommunications technology being put into what is essentially a life safety device to help the operator. And that kind of continues that common theme. I'm just going to stop sharing for a minute just so I can see the chat. There's no questions. I see Eva answered one previously. There's no questions coming in at the moment. I think people are still digesting what was a great presentation, Reda. from my side, just a question around the connected element. So my specialism is CBRN, so I can see the benefits of the connected safety element, because if you've got to put yourself in that hostile environment, the individual wearing it is often under a high stress situation. So having that connected backroom view of the world is really important. But do you think there's is it a fine balance between adding too much technology to the system, or do you go through a design process? You're on mute, Reda.
Sorry. Yeah, thank you, Dave. Yeah, it goes through a lot of design process. Obviously, when we look at industrial workers, firefighters, they carry a lot, on the fire suits, on SCBA, and then rescue tools, and a lot of kits around that. Here, what in this kind of connected systems we are trying to do, we know the firefighters at the field, we know the safety workers at the field, they are trying to get into specific tasks, but we don't know exactly what sort of situation they are going through. So this connected system really helps to increase visibility, and also improve situational awareness for the people remotely monitoring. And of course, the whole objective is to ensure seamless link and connectivity solutions here. It is not really adding more challenges around the workers at the field, but making them very comfortable and focus on what they are assigned to at the field, and leaving some of the instructions coming from them, better user interaction, receiving two-way communications, also sending message to remotely, and also receiving messages from remote. So that helps you a lot. And then the design process in terms of connectivity helps to solve so many challenges for the workers at the field. That's how we are looking at it there.
Okay. No, that's very good. Thank you for that. Thank you, Eva, for putting it in the chat. So apologies, Tim. So there's a question. I guess it's for all three panelists now, as we're into the Ask the Expert session. It's from Tim Paz, and he said, has anyone conducted research on the effects diaphragmatic breathing and or mindfulness practice has on one's physiology and psychological ability in wearing a respiratory protection device? I think that's a really good question around kind of, because no one likes wearing respiratory protection. I suppose after many years you get used to it, but you're still not comfortable with it. So has anybody, did you, and again, this is for Eva and Dan as well as yourself, Reda, has anybody done any research into this that you're aware of in terms of mindfulness practice around the physiological and psychological ability of wearing RPDs?
Dan here, I have to admit that I'm not quite sure what mindful breathing means. It sounds like a nice concept, but I don't know what it means in practice. So I'm not a good person to answer that question, I'm afraid.
Okay, I'll just see if Tim, let's find Tim in the chat. I'm just gonna, do you want to answer? I'm allowing you to talk, Tim. Do you want to answer ask the question? Okay, I think I get the angle of the question. So mindfulness is around when you put yourself in, when you're feeling stressed, it's kind of the close your eyes, sense your body, feel your breathing to try and bring your mind into the present rather than kind of let your mind run away with you into dark thoughts, etc. So from that respect, I guess it's around the psychological burden of wearing RPDs, especially from a RIDA perspective, when you're having to wear SCBA And again, you use two very good examples of phosgene and hydrogen sulfide. If you're working in, say, an oil field where you know it's very, very high concentrations that are potentially fatal.
Yep.
I would just like to say that although I cannot answer this question scientifically, I can answer it anecdotally, which is that I do that when I wear a respirator, and it really does help. So same techniques that you can use to control your breathing when you're anxious in normal life and diaphragmatic breathing, it really does help when you're breathing through a respirator as well.
I guess, Tim, we've kind of partially answered your question, but I think that's one to take away and look at and try and answer at a later event. So if in the interest of time, I cannot see any more questions in the Q&A. I think all three have covered your subjects very, very comprehensively, which was fantastic to see from an audience perspective. So with that, I would like to thank all three of you for today's inputs. Very much appreciated by the whole section. Just before I close the proceedings, just to let you know the future webinars for this year. So the next one, the registration is already open. You can find it on the ISRP website. Is on respirable crystalline silica on the Thursday, the 13th of October, at the same time as today. And then on 24th of November, we have one on welding, and that covers the European Welding Federation as well as the Breathe Freely campaign. So those webinars are available to register for. So we look forward to seeing you then. In terms of today's webinar, it is recorded, so it will be available to ISRP members online, as will the presentations. So with that, I would like to thank everybody for attending, in particular our three keynote speakers. I thought it was three very excellent presentations. And with that, I wish you a very safe journey home, or if you're already at home, have a great rest of your day. And we will speak to you soon. Bye-bye.
Thank you. Thank you.
Thank you.
Bye-bye.